Hello. I hope you're doing very well. Okay, we are done with test number 3. So what we are going to do is we are going to have another quiz number 4, and the final. So I'll try to, when try to post the final review for you. The final review would be mostly the final exam would be mostly whatever we did for the test. Okay, test 3, and just a couple of more ideas that we're going to talk about it. What I'm going to do now is I'll just give you the idea of it's in section 5 point, I think it's in the 5.3. So we're just dealing with the complex from time to time. Of course, we talk about the real, we were working with the real number system. Remember, especially when you're dealing with the matrix, you are interested in finding the eigenvalues. In order to find the eigenvalues and eigenvectors, you need to solve an equation. That equation is, maybe, okay, 2 by 2 matrix, quadratic one, then the cubic, etc. But if you stay in the real system, you know that some equation may not have any solution, any real solution. So if you get any real solution, then you don't have any eigenvalues. So in science, they base the domain on the complex numbers. And the reason is when you get the complex numbers, then any characteristic polynomial, or in fact any polynomial of n degree would have n solutions. But some of the solution can be complex numbers. So some of these eigenvalues may be complex. So we don't want to get into the more details of the complex space. In future, if you need it, you will have it in your special fields. But we would like you to be able to handle some easy matrices with the complex eigenvalues. Okay, so we get a complex eigenvalue, so you're going to have a vector. That vector maybe is not going to be in real space. Is going to be in complex space. So like the one that we did R2, R3, R4, you are going to have a similar one for the complex numbers. So we want to give you briefly some ideas on how we're going to handle this. We need it because what I would like to do is I would like to give you an application of these eigenvalues. And the best application is when are we going to solve a system of differential equations. You don't need much great calculus to understand it. If you already done differential equations course, they discuss it, or sometimes they avoid it because there are 2 different methods to do it. But it's very nice application of the eigenvalues. So we are going to nearly end up with considering those type of problems for the rest of the course. So just there was something that I give you a question on the test, and we're going to repeat it again on the final. That's the power of a matrix. Some of you were not feeling very well on that one because we didn't talk about it directly, in fact, honestly. So I'm going to give one example of that because there was one on the test, the last question, and there is going to be one on the final, okay? So let's take this one first. This is from 5.2 again. If you want to find the power of a matrix, of course, we can use our calculator to find it. But what would you like to do? Would like to use the diagonalization of a matrix to find the power. So they are going to guide you, give you the hint that of course you have to use this method to get it. Okay, it's a very popular example, and we did one on the test, and it's going to be one on the final. I want to make sure that officially we have it here. Okay. So this is going to be a situation that we are going to have. I set up my position and then we go for it. Okay, so this is part of, again, it must be discussed from 5.2. So just make sure we have it. Again, part of this. And what is this one? This is just the power of a matrix. Okay, so how we're going to define power of a matrix by this new method that we have. You know that if you have a matrix and if it's going to be a nice one, we can find a similar diagonal matrix to it. So we want to use that one, okay? So suppose we have a matrix. Suppose the matrix A, the matrix A is given. The matrix A is given, and we know that this matrix has already been diagonalized, and the diagonals, we have a diagonal metric, and this is going to be P inverse of AP. You know that you find the eigenvalues, you put the eigenvalues in the main diagonal of the matrix D, and then this is going to be matrix P. The column of a matrix P are just eigenvectors. So if this is going to be the case, then suppose you want to raise it to something, okay? So suppose the matrix A is given, and this is going to be the case, then for any, if you give me any number, for any, okay, for any positive integer, okay, integer k, then I can find the d to the k is going to be P inverse of the AP to the k. Okay, so if you want to get it, you have to distribute it. It's going to be P inverse AP, then you multiply by P inverse AP again, okay, and then you just continue. You continue to get to the P inverse AP. Okay, now if you reorder it, you will see that you see these numbers. This P and P inverse would be identity, and you just keep going. So what you're going to have, this would disappear. When it would disappear, that give you a here, and you do the same to the second one. So you just continue. So what you are going to get is this one. The P inverse would stay. Okay, we get this one. So we get the P inverse, okay, as is, but the leftover is going to be the P inverse. But in between, these are going to be disappear. So we're going to get what? We are going to get the A. Okay, and at the end, we are going to be getting, getting the P here. So anything in between this P inverse would be identity, would disappear. And this is going to be, of course, okay, this is going to be, of course, K times. That give you K times. Okay, so the result is going to be, P inverse of the A to the K times P. So that would be a very nice result. So what we have is D to the K. D to the K is equal to the P inverse of A to the K, okay, A to the K times P. Now, P is invertible, we can solve for A to the K. In order to solve for A to the K, you have to get rid of the P inverse and the P. So I multiply from the left by the P, from the right by the P inverse. So that give me what? Give me P D to the K, and this is going to be the P inverse. And then I have the P inverse A to the K, P inverse. Again, these are going to be disappear. Okay, this is going to be identity, and this is going to be also an identity. Okay, so what is going to be the result? The result is going to be the P D to the K P inverse. Okay, and the result is going to be simply A to the K. So you have a nice formula for the power of a matrix A. So the power of a matrix A to the K, is going to be P D to the K times P inverse. Okay, and you know that this is a diagonal matrix. If you want to raise the diagonal matrix to the K, you're simply raising the terms, the numbers on the main diagonal. So we can easily finding the power of a matrix A using this diagonalization, if you like to get the result. Okay, so this is the one that we are going to be interested in. Okay, you did have one on the on the test. So we give you another one, and this is the way they are going to guide you to show you that you must do this method. So this is a kind of example that you are going to see again on the final. So they give you a matrix. You see, suppose and the matrix A is given. This is going to be A, and you have the 10, 18, -6, and the -11. Okay, this is given. Then they divide in two parts. The first part is just diagonalizations. They ask you to find, find a matrix P, a matrix P that diagonalize. Okay, diagonalize A. Okay, this is going to be the case. And the second one, now they give you the hint. Okay, so now you're going to diagonalize A if you like. You're going to do this one and compute, because you need this one, and compute as usual P inverse of AP. And the part B, they ask you to use the part A. Use part A to compute. Okay, to compute A to the 6. Or basically, as I gave you on the test, they just ask you use diagonalizations to find A to the A to the 6. Okay, so we need the part, we need the P. You need the P and the eigenvalues. So let's go and find it first, and we come back, we know the formula for A to the 6. You see A to the 6 going to be P D to the 6 P inverse, and then we'll be able to find it quickly. Okay, so let's go on and find the eigenvalues and then the eigenvectors to get these numbers. Okay, so this is going to be the situation that we are going to have. Okay, so the solution is going to be, this is it. This is going to be the solution. So we are going to find eigenvalues and eigenvectors first. Okay, find all. Okay, eigenvalues and eigenvectors. Eigenvectors corresponding to those eigenvalues. Okay, so this is it as usual. Okay, that's going to be the one. So we are going to find determinant of the, that of lambda I minus A equal to the 0. So we get that determinant, this is it. So we get the lambda minus, what was the A? Minus 10, you switch the sign here, that make it to the positive 18, negative 18, yes, that was the 18. So that would be negative 18, and this is going to be the 6, and the lambda plus 11 equal to the 0. Okay, so get the determinant, lambda minus 10 times lambda plus 11. Okay, you multiply these together, the sign is going to be positive. 6 times 8 would be 48, that gives 108. And equal to the 0. So simplify this one, it's going to be FOIL method. Lambda squared plus 11 lambda minus 10 lambda minus 110. And we get 108 equal to the 0. If you simplify that, give you lambda squared. Okay, that gives you lambda squared plus lambda, and this is going to be minus 2 equal to the 0. Okay, 2 equal to the 0, we factor it. We get lambda plus 2 times lambda minus 1 equal to the 0. So we have two lambdas, okay? So lambda 1 is equal to the negative 2, and lambda 2 is equal to 1. Okay, so we get two eigenvalues here. Okay, so we are going to find the eigenvectors one by one. We start with the lambda 1, lambda 1, lambda 1 equal to the -2, and we are going to solve this equation, lambda I minus A. Okay, lambda I minus A times the vector X equal to the 0 when X is, as usual, is going to be X1 and the X2. Okay, go back and substitute quickly to get that matrix. It's going to be the matrix. We replace the lambda here. Okay, we replace the the lambda by the -2. So that give you what? That give you -2 minus 10. -2 minus 10, and then this is just a -18. And this is going to be the 6, -2 plus 11. Okay, times it by just the x1 and the x2, which is going to be equal to the 0. We simplify it. Okay, when you simplify it, that give you on the top, you get the we get the -12, -12, -18, and this is going to be simply 6 and the 9. And this is it, x1, x2 equal to the 0. Okay, we already talked about it. You know that one of them is a factor of the other one. So we're just using one of these rows and we take care of it right away. Okay, I just use with the second one, just multiply. You don't need to simplify it because we know that this is going to be a dependent system. So I go with the 6x1 plus 9x2 equal to the 0. So I divided by 3, so that give me 2x1 plus 3x2 equal to the 0. Okay, just solve for one of them. Okay, so for example, if you solve for x1 or x2, it doesn't matter. Okay, so I have the x1 is equal to the -3/2 of the x2. You have to take one of them to be optional. You know, in order to get rid of this 2, we can take it to be what? Take the x2 or just the t, then take care of it. Okay, it doesn't matter. So if you take the x2 to be equal to the t, and so the x1 is equal to the -3/2 t. Okay, 3/2 t. So the eigen vector, we call it p1 because this is going to be the column of that matrix that we're going to use. Okay, so this is going to be what? It's going to be -3/2 of the t and the t. Just pick a nice number for the t, for example, t equal to 2 because we need one of them. So that gives us a p1 is equal to, okay, is equal to the -3 and 2. So this is going to be, okay, the p1, the first column of a matrix P. Okay, so that's going to be the eigenvectors related to the lambda 1 equal to the -2. We do the same to find the lambda 2. Okay, so there you are. We continue. So we go with the second one. So the lambda 2 is 1. Lambda 2 is 1. So we are going to form again lambda I minus A times x equal to the 0. Okay, x equal to the 0. And then we are going to substitute again. If you substitute on that matrix form that we have, it's going to be 1 minus 10. Okay, 1 minus 10 this time is a -18, and the other one was 6. And this is going to be 1 plus 11. 1 plus 11 times the x1 and the x2, which is equal to the 0. Okay, so that gives you a -9 and -18, and this is going to be the 6 and the 12. Again, they are multiple of the other, so this system is going to be dependent. So we can take one of these rows and multiply, get the other one. So I'm going to stay with this one. So that gives me 6x1 plus 12x2 equal to the 0. Divide by 6, so that gives me x1 plus okay, 2x2 equal to the 0. So x1 is equal to the -2x2. So we take the x2 to be equal to the t, so x1 would be negative 2t. So we are going to have eigenvector, we call it p2. Okay, so the p2 is going to be negative 2t and the 1. So we just pick one of them for t equal to 1, for example. So the p2 is going to be negative 2 and 1. Okay, that's it. So we are ready to give you the matrix P and the rest, and we are ready to get the power. Okay, so there you are. The matrix P is going to be just the P1 and the P2. So the matrix P is going to be equal to the P1 is a negative 3 and 2, and the P2 is just a negative 2 and negative 2 and 1. Okay, that's going to be the P. Now, we need the P inverse because of that power that we talked about it. Okay, so you better find the P inverse to make sure that we are ready for it. Okay, you know there's a 2 by 2 matrix, and we can find the P inverse quickly. So what's going to be the P inverse? Remember, you need the determinant of this matrix quickly to find it. So what is going to be that of P? That of P cross multiply, so that give a negative 3. And this is going to be minus, and that make it to the plus 4, which is equal to 1. So the determinant of the P is 1, and we can find the P inverse quickly. P inverse is going to be 1 over the determinant of the P, which is going to be 1 over 1. And you know that you switch these diagonals, it's going to be 1 and then negative 3, and just change the signs, negative 2 and the positive 2. Okay, so this is going to be P inverse. So the P inverse is 1, 2, negative 2, and negative 3. Okay, let's go on P inverse. Okay, that is going to be the P inverse, and the matrix D, we know that the matrix D is going to be matrix whose diagonal are going to be, okay, I write it down so that remember, lambda 1, 0, 0, lambda 2. So in this case, this is it. So your matrix D, lambda 1 and the lambda 2. So it's going to be negative 2, negative 2, 0, and the 0 and 1. Okay, so we have everything we need. So I just go with the power. I'm just checking those diagonal. It's clear that it's going to be diagonalized. Okay, so there you are. Just remind you that the P inverse of the AP is equal to the T. As we talk about it, if you want to find the power of the A, okay, so how we're going to find that power of the A? Okay, so this is it. So power of the A, we do the other way around. So we solve for A and we take that power, okay? So this is it. A is equal to the PDP inverse. Okay, so you want A to the 6. So it's going to be P D to the 6 P inverse. So this is how we're going to find this, this power. We substitute and we get it right away. Okay, so you have to find those the diagonal matrix to get this number. So let's find out. So what is going to be A to the 6? Okay, so this is it. That would be easier to get this one. Okay, so there you are. What is going to be A to the 6? So A to the 6 is equal to, okay, is equal to I just repeat it again so I have it here. So remember that is going to be PD P inverse, PD to the 6. So it's going to be equal to, the matrix P is negative 3, negative 2, okay, 2, 1, times it by the matrix D, just a negative 2, 0, negative 2, 0, 0, 1 to the 6, okay, times 1, 2, negative 2, and negative 3. Okay, that's it. The middle one is a diagonal matrix, so easily can be computed, the power. is a -3, -2, and this is going to be 2, 1. Okay, 2, 1. To the 6 is going to be -2 to the 6, okay? And -2 to the 6. 2 to the 5th would be 32, is going to be 64. And 0 to the 6 would be 0, and that would be 0. And this is going to be 1. Okay, for the diagonal matrix, this is what will happen. And this is going to be 1, 2, -2, and -3. You see? Very easy matrix to, okay, to multiply together. Okay, to get these numbers. And you can multiply the first two, and then you get the last one. Okay, so this is it. If you multiply the first two and get okay, that's 1, -3, then 64, and this is it. So this is going to be the case. So -3 times 64, and that gives you what? Negative is going to be -3 times 4 would be okay, 12. 3 times 6, 18, 19. So this is going to be the case. So -3 times and the 2 times 0. And for the other parts, the -3 times 0 would be 0, and then -2 times 1 would be -2. So that gives you a -2. Okay. And for this one is a 2 times 64 would be 128. 128, that would be 0, nothing. And over here, that gives you 0, 1. Okay, 0, 1, and then you multiply by 1, 2, -2, and -3. Okay, this is going to be the case. So it's going to be equal to, again, you multiply by this one and the -2 up. So that gives you, okay. So that was 2 times 60. Just check this one again. So that gave me 12, and that's going to be 18, 19. Everything's all right. So over here, oh yeah, that's going to be, so this is going to be -192, and this is going to be minus, okay, which one? I just want to check, make sure the sign that I got over here. Okay, so I get this one, and then I go to the next one, and this is a -2. This is a -2. Okay, so negative would be positive. So eventually it's going to be -188. Okay, if we multiply, the other one is -388. And this is going to be 126 and the 256. You can check it, you know what. This is going to be a to the 6. Okay, so this is how we are going to use diagonalization in order to get the power of a matrix. Okay, just want to give you an example. Make sure that you are going to do this problem on the final for us. Okay, so that's the powers of a matrix. Now, the idea of this bringing the complex, okay, if these eigenvalues, in future, this is finite dimensional space. You see, in finite dimensional spaces, you can use this idea of we use matrices. But when you go to the infinite dimensional, you are not going to use the matrix. You are going to use linear transformation. In the case of the linear transformation, then we extend the domain to the complex numbers, okay, so that we make sure that we get these eigenvalues. Now, you know that we assume that we are familiar with the generally complex numbers. We know that it's a form of a plus bi. Then you have a real part, imaginary part. So we can do the same thing with the with the matrix. I'm going to explain more when we get to those system of the equation, but for the time being, we are going to be interested in a matrix. Okay, we get a matrix, entries of the matrix, the numbers. The entries of a matrix are real numbers. Okay, the entries are real numbers, but when we want to find the eigenvalues, we find out that one or some of the eigenvalues are going to be complex numbers. Okay, so this idea is going to be how we're going to deal with a matrix whose entries are all real numbers, but we get to the complex solution, complex eigenvalues. Okay, so we give you a theorem regarding this one and we take care of it. And most of the matrices that we are going to have is of this format. Okay, so this is just one part of 5.3 that we're going to cover. There are quite a lot in 5.3. You are interested, you can read it for yourself, but part of your program is going to be just, easy case. And then we need enough information to be able to solve those differential equations. So what we are going to be interested in is going to be, as I told you, this is it. We are interested in complex. Okay, we are interested in complex complex eigenvalues. Complex eigenvalues are real matrices. Real matrices. So our matrix for this theorem, our matrix is not a complex matrix. A complex matrix would be a matrix whose entries can also be complex numbers. We don't have any complex numbers for the given matrix, but when we find the complex values, we find out that we are going to get to some complex eigenvalue. Let's try to see if I can get a better focus for this. Okay, let's try. Yeah, that's better. Okay, so this is going to be the idea of complex eigenvalues of a real matrices. Now we have a theorem. What is this theorem? Quite an interesting one. Okay, this theorem will tell you that if one of your eigenvalue happen to be a complex numbers. Okay, so if lambda is going to be a complex a complex eigenvalue of what? Of a real n by n matrix A with its eigenvalue. So you should be able to find the eigenvectors with the corresponding eigenvector x. Okay, that's going to be the one. So we find the eigenvalues. Lambda happen to be a complex numbers. Then we go ahead as usual. We can, it's a similar method. It takes a little bit more time. But it's a similar method that enables us to find the x, which is going to be eigenvectors. Of course, that eigenvectors also is going to be a complex vector. Okay, if this is going to be the case, that's important for us. You see, then the conjugate of the lambda bar. Remember the conjugate of complex numbers? If you have 1 plus 2i, the conjugate would be 1 minus 2i. So that's complex denoted by lambda bar. Okay, conjugate. So then lambda bar is going to be also an eigen. Okay, and also an eigenvalue of a, and the conjugate of the x bar is going to be a corresponding eigenvectors. You see, that would make your job easier. It's nothing new, really. You see, when you solve an equation, if you solve an equation in algebra, if you solve a quadratic equation or any equation, if your solution is going to be complex numbers, we say the solution comes in pairs. So this means if lambda is the solution of your equation, then its conjugate, the lambda bar, is also the case. When you use quadratic formula, remember quadratic formula is what? Is the negative b plus or minus radical b squared minus 4ac. If it's going to be complex numbers, if one of the solution is 1 plus 3i, automatically 1 minus 3i would be also a solution. So that will help us quite a lot. So as soon as you find one of the lambdas, automatically you have the second one. And as soon as you find the x, the vector corresponding to the lambda, you take the conjugate and they give the second one. Okay, so that makes things easy for us. And this has happened for a matrix with a real, okay, it's very easy to prove. If you know a little bit about the complex numbers, it will prove it for you so you can see it. This is going to prove, easy to prove. Okay, just use the definition. Suppose lambda is the case. You see, this is it. Suppose lambda, okay, suppose lambda is an eigenvalue of A, and okay, and x is its corresponding, okay, corresponding eigenvectors, eigenvector. Okay, so what does it mean? So what's the definition? So then you see the definition of the eigenvalue. You know that A times x is equal to what? Is equal to the lambda x. That's the definition of eigenvalues. Now take the conjugate. They are complex numbers. So take the conjugate of both sides. Means the conjugate, the bar, the conjugate of A times AX equal to the conjugate of the here. The conjugate of a complex numbers are multiplicative. This means you can break it. Or you can break it. It's going to be A bar, the conjugate of a matrix, times the conjugate of the x bar, is equal to the conjugate of the lambda, which is lambda bar, the conjugate of the x, which is x bar. You see that's one. But remember the matrix, your matrix, your entries are real numbers. So when you want to find the conjugate of a matrix, you just take the conjugate of each entries, the numbers inside. But the numbers inside are all real numbers. So this means this conjugate would be the same. Say, oh, but the entries, if you like, A is a real matrix. A is a real matrix. There's no complex numbers here. Real matrix. And so the conjugate of the A and the A are the same. So what does it mean? This means here A x bar is equal to the lambda bar x bar. And you know what does it mean? This means lambda bar is a eigenvalues and x bar is its corresponding eigenvectors. This is what we want to prove. So this means, okay, lambda bar is an eigenvalue and x bar is its corresponding vector. Corresponding eigenvector. That's it. That's proof of this theorem. Okay, so that make it very easy for us. So as soon as you got a complex number, a complex eigenvalues, you find the corresponding eigenvector, then you make a conjugate of these two and you're done. You see, you have extra one free, okay? And that will help us quite a lot to do the problem with the, okay, with the complex eigenvalues, okay? It takes a little bit time if it's going to be 3 by 3, but we practicing these on 2 by 2. Just want to get the idea really, okay? So that's it. We give you one on the final in the next quiz and the final. So what is this? Example. Example, we wanted to find, as usual. You know, you can do the diagonalization, everything we did with those type of ideas. It's going to be the same thing here. Okay, find the eigenvalues. The eigenvalues. And they say, and the basis. And a basis for the, okay, for the, they call it eigenspace. Eigenspace is going to be those eigenvectors plus 0. And that's going to be 1. But we usually go with the eigenvectors right away. But this is the expression of your book. Find the eigenvalues and the basis for the, okay, for the eigenspace. For the eigenspace of the matrix. So basically find the eigenvalues and eigenvector. So what is that matrix? Matrix A is equal to, there you are. Matrix is a -1 and -5. Okay, and we have the 4 and 7. That's it. Okay, so as you see, I can see the terms of this matrix, they are all real numbers. There's no complex numbers for the time being, you know, you won't see it. But when you try it, then you may get it. Okay, so this is going to be the one. So far, when it seems to be something similar to the, okay, to the whatever we did before. Okay, but as soon as we start working on those characteristics equation, we realize that we get to the, okay, we get to the complex numbers. Okay, so let's see when we get to, okay, we get to that one. Let me see that what I have. So make sure we get the correct one. Okay, there you are. Let's go for it to see when we get to that number. Just want to make sure I have the correct one. Yes, this is one of the one that we are interested in. Okay, so let's go. Let's find out. You know that we have to go for the eigen as usual to see when we get to those complex. Solution. What you do, you have to form the determinant of the lambda I minus a equal to the 0. As usual, this is going to be the determinant. This is a lambda plus 1. This is going to be a positive 5. This is going to be a negative 4. And this is going to be lambda minus 7 equal to 0. Okay, find the determinant, cross multiply. Is going to be lambda plus 1 times lambda plus 1 times lambda minus 7. Okay, lambda minus 7. And that gives you negative 40, but there is a sign here. Okay, 20 plus 20 equal to the 0. Okay, FOIL it. So this is going to be lambda squared, lambda squared minus 7 lambda. Okay, minus 7 lambda and plus lambda and minus 7. And we have a 2 here equal to the 0. Simplify that, give us a lambda squared, and this is going to be negative 6 lambda. Okay, minus 5 equal to the 0. Okay, you cannot factor it because you need two numbers with the product of 5 and a difference of 6, which is not possible. So you have to use quadratic formula to see what is going to be the, okay, the situation we're going to have. Okay, so you can go with the quadratic formula right away, or I usually find the delta first. It doesn't matter. I go with the b squared minus 4ac first to test it, or you can go ahead write the formula. So this is going to be a negative 6 squared minus 4 ac 1 times a negative 5 So that make it into the positive 36. Okay, this is going to be, so what I'm going to have is, this is going to be a 36. Did I miss anything? Yes, this number must be good one. You see 5 times 4 is 20, because I need the complex numbers here. And this is 20. Okay, and so this is going to be a positive 13. Otherwise, you won't get it. Positive 13. Okay, so I go to the next page and explain this one again. So lambda squared minus 6 lambda plus 13 equal to the 0. This is what we have. Okay, so rewrite it. This is, so I take it from here that I have this equation to solve, lambda squared. Okay, lambda squared minus 6 lambda plus 13 equal to the 0. You can directly write the quadratic formula if you like, but you know, I just do it briefly so I make sure I'm not making any mistake again. So it's going to be negative 6 squared minus 4. Okay, it's going to be minus 4 times 1 times 13. So that give me a 36. Okay, this is a 36 minus, okay, and this is going to be minus 52. Okay, so the 36 minus 56, which is going to be negative 16, and this is what we are interested in. Okay, delta equal to the negative 16, it is negative. You know that when the discriminant is negative, your solution is going to be complex. So this is going to be your solution. See, lambda equal to, and negative b is a negative negative 6. Okay, plus or minus the square root of negative 16 divided by 2a, which is going to be 2 times 1. So we change the negative 16 to the 16i squared. So this is going to be a 6 plus or minus radical 16i squared. Now we know the complex number. So if it's going to be everywhere we see it, we know that we have to continue. Okay, that's going to be 2. Now, so lambda is going to be equal to, the top is going to be 6 plus or minus, okay, 6 plus or minus 4i. 4i divided by 2. Okay, divided by 2, we break it to simplify it, so that gives us a 6 half. 6 half plus or minus 4 half times I. So it's going to be 3 plus or minus 2i. So as you can see, you have two complex numbers, plus or minus 2i. And they are conjugate of each other. You see, one of them is 3 plus 2i, the other one is 3 minus 2i, which is going to be now the conjugate of the other. Okay, so if you like, your lambda 1 is 3 plus 2i, and your lambda 2 is 3 minus 2i. As we talk about it in the theorem that we have, okay, when 3 plus 2i is an eigenvalues, its conjugate, which is 3 minus 2i, is also, okay, the case. So what we have to do is we have to find the eigenvectors for this one. As soon as we get the eigenvectors for this, then we try the conjugate gives us the other one. Okay, now how are we going to find that eigenvectors? Okay, so there you are. As usual, as we did it before, you see lambda 1 is equal to the 3 plus 2i. So you have to form what? Lambda I minus a times, okay, times x equal to the 0. When x is, as usual, a vector x1 and x2. Now we have to form lambda I minus a, but you have 3 plus 2i. Remember the way we did it before? We usually go to this form and here, and we put the lambda. Okay, so the lambda is 3 plus 2i. So we have to substitute it here, and then you continue. Okay, so this is going to be the case when you substitute it. So it is going to be you're going to have a matrix lambda minus a. So the lambda is 3 plus 2i, 3 plus 2i, and the term for a over there was -1, make it a +1, +1, and the other part was just a 5, a +5, and this was a, okay, this was a -4, -4, then again lambda. Okay, it was lambda, which is a 3 plus 2i, 3 plus 2i, and it was 7. Now to make it to the -7. Okay, we substitute as we did it before, but this time we have a complex number, so it's not a big deal. Okay, so this is going to be times a vector. This is going to be x1 and x2 and equal to the 0. Same thing as we did before. So we simplify this one, the complex numbers, the real part, you can add them together. So 3 plus 1 would be 4. You see that give you 4 plus 2i. And this is going to be just 5. And over here, this is going to be a -4. And this part over here is going to be a -4 plus, okay, -4 plus 2i. Plus 2i, and this is going to be the x1 and the x2. You see the same situation that we did have for the other ones. For the other one, we just have a look and quickly we say what? We say that, oh, one of them is the multiple of the other ones. It is the case for this one too. I'm going to do it for you, but you don't have to do it. Okay, you can pick this one. Okay, you can pick this one. Let me just write it down, then I show you that, you know, it's true. So it is true that we can show that this is going to be multiple of the other one. We can change it to the real, you know, just echelon form, and you make this one 0, 0. But in practice, use as we did before. You multiply these, okay, so that give you what? That give you a -4x1, and this is going to be -4 plus 2i times x2 equal to the 0. You see, that's our claim. Then you have to find this x1 and x2. You need a little bit of work to do. So what you do, you just move one of them to the other side and find the x1 or x2. It doesn't matter. Okay. So this is it. I keep this one, or just the other one. It doesn't matter. So in that case, you are going to get the, both of them are going to be the same. We try to avoid the complex numbers, so we divide by 4. So I move this 4x1 to the other side. So this is going to be -4 plus 2i, okay, times x2. Okay, I just move this one to the side. Then I divide by 4, so that gives me x1 equal to the -4 plus 2i divided by 4 times the x2. And this is kind of complex number, so we just divide by 4, divided to be able to do it. So it's going to be, you see, this is like a -4 over 4, and this is going to be a 2i over 4 times it by x2. Okay, so it's going to be x1 equal to what? It's going to be equal to the -1 plus 1/2 of I times x2. You see, there are some nitty-gritty one that you have to consider. And so this is it as usual. You can take one of them to be arbitrary and find the other one. So I take the x2 to be equal to t. Okay, x2 equal to the t. So my x1 is going to be equal to the -1 plus 1/2 of I times it by t. Okay, times it by t. So now I'm ready to give you my first okay, eigenvector. I'm going to denote by p1 because sometimes it's used for the diagonalization. So I call the first one to be p1 if you like. So the p1 is going to be what? Is going to be the x1 and the x2. Okay, this is going to be the case. So I go to the next page, so because I have to explain the P22. Okay, so this is it. Let's go to the next page and identify these eigenvectors. So we have the P1, which is equal to the x1 and the x2. So this is going to be equal to, so what we did over here, x1 -1 plus 1/2 of I, -1 plus 1/2 of I. Okay, this is times t, and the other one is t. Okay, you can factor out the t out. So it's going to be t, and this is going to be a -1 plus 1/2 I, 1/2 I1. Okay, pick a t because we need one of them. Okay, so if you pick t equal to 1, if you pick t equal to the 1, you are going to get your P1. So that's going to be the P1. So what is the P1? The P1 is -1 plus 1/2 of I times 1. Now we have to write this one as a kind of a complex vector. You have to break this one, that real part and imaginary part that we have for complex numbers. So it's going to be equal to what? It's going to be equal to, if you break it, the real part is going to be, you get the -1 and you get the 1 here. Okay, that's the real part. This is going to be plus, and the leftover, okay, this is going to be 1/2, and there is no I here, so it's going to be 0 times it by I. So this is going to be your eigenvector, if you like, corresponding. So usually you have to break it. And so this is going to be, it's going to be a complex vector. So you have the real part and the imaginary part. It's going to be 1/2 of 0 I. So this is going to be, okay, this is going to be the eigenvector. Eigenvectors corresponds to what? Correspond to the lambda 1. So you have to find another one. Remember, we have two. So what we are going to do, we use the theorem that we talk about it. We are going to take the conjugate of this to get the second one. So we take the conjugate, so P1 conjugate is going to be the conjugate of this. You just change the middle sign of the I. Okay, so this is going to be -1, 1 unchanged, but this is going to be minus 1/2, 0, and I. So this would be your P2. Okay, second eigenvectors. So this is going to be a -1, a 1, minus, okay, 1/2, 0, and I. You see, this is going to be, this is the, if you like, this is going to be the eigen, okay, this is going to be the eigenvectors. Remember, you see, this is the, if you like, by your information, this is going to be eigenvector corresponds to what? To lambda 2. Remember, the lambda 2 was 3. You see, that was the lambda 1 that we find. 3 plus 2i, this is 3 minus, okay? 3 minus 2i. So that's how you take care of this real matrices when when we try it and we get the complex solutions. Not a big deal. You see the complex solution, we just do the same thing that we did before to get this true. So as soon as you got as soon as you get this complex solution, you come back and you form these lambda I minus a x equal to the 0 as we did it. You see, this part I'm going to show you. You don't have to show it on the test, but I'm going to confirm you, to convince you, if you like, that if you just do because officially, that officially you have to change this matrix into the row echelon form if you like, and then get the job done. So for the real case, you see that one of them is a multiple of the other one. You may not convince here, so I just show you again. You don't have to do it on the test. Okay, so as a remark, look at this remark. So I take it from just at the beginning that I have, and I change it. So it's a 4 plus 2i 5. You see, that was the one. You have a 4 plus 2i, and that was 5, and the other one is what? Is a negative 4, and this is a negative 4 plus 2i. You see, that was the one that I started with. Okay, and this is the one that we call it x1, x2. Okay, I just picked the second part, and I didn't bother. Didn't bother to prove something or anything. But I wanted to show you that this is going to be the case really. See, I picked this one. Now, officially, if you want to do it, you know that you have to change it to the row echelon form. Okay, so the row echelon form is going to be, you need a 1 here. Okay, you need the 1 here and the 0 here. So to get the 1, you can quickly divide it by 4 plus 2i if you like, or what can you do is you can simplify it a little bit. You add these two together. Okay, so it's going to be, what I do, this is the R1. I write that as R1 plus R2. Okay, so this is going to be the result. So negative 4 and positive 4 would cancel out. So I end up with the 2i. Okay, the 2i, and then I add these together. You see, if you add them together, this is a negative 4 and a positive 5 that give you 1. It's going to be 1 plus 2i. 1 plus 2i, and over here we have a negative 4, and we get the negative 4 plus 2i times the x1 and the x2, which is going to be 0. Okay, this is a kind of another option. Then you have to make this one into 1 if you like. If you want to make it to the 1, then you have to divide by 2i. So this is going to be r1. We change it to the r1 over 1 over i r1. So what you are going to see is you have to simplify it a little bit. So this would be 1, but this would be 1 plus 2i divided by 2i. Okay, and this is going to be your negative 4, and your negative 4 plus 2i. Okay, then this is going to be the case. So you get the 1 here. Okay, you get the 1 here. So what you are going to do, you have to change this one into the 0. To change this one into the 0, you have to have the R2. You write the R2 as, okay, plus 4R1. Okay, again, this is going to be just to convince you that that method was correct, but it takes time to, if you want to do it. So the first one is unchanged. Okay, this is going to be the case. I have the 1 plus 2i over 2i. So when I add, this would be 0 as I like it. Okay, and how about this one? If you multiply this one by 4 and you simplify it a little bit, okay, this would be simplified. So you have to simplify it outside to do it. You see, this is going to be the case. It's going to be R2 is a negative 4 plus 2i. Okay, this is going to be plus 4 times. If you say 4 times, these two would simplify it a little bit. So we get the 2 times 1 plus 2i divided by I. then you have to simplify it. It takes time. So this is a negative 4 plus 2i, and this is going to be 2 plus 4i over I. Okay, and we can simplify it further if you like. So this is going to be a negative 4 plus 2i. Okay, you break this one into the 2 over I plus 4i over, that give you 4. 4 and 4 would cancel out. Okay, this is 2 over I. The C4 and 4 would cancel out. Then you simplify these two. You see, these two would be I. You multiply the top and the bottom by I, so that give you 2i minus 2. Okay, so the simplification of this part together, you end up with the 2i minus 2. You see? You better accept that one that I talk about it. You see, that's going to be 1. Then you have to make this one into the 1. To make it into the 1, you have to divide by, that would be easy to divide. Okay, so that's going to be the R2. You change it into the R2 divided by 2i minus 2. And eventually we get the, okay, we get 1. So it's going to be 1. And this top one, okay, the top one is going to be 1 plus 2i over 2i. And we get the 0 and 1. Okay, we get 0 and 1. And just one more step to go to change this one into the 0. You have to simplify the top one. It's a long argument, but it is going to be the same thing. Okay, so I divide to get the 1. So one more step, just a little bit more step to make sure that this is going to be 0. So I go to the next page. I wanted to convince you really. That is the main thing. Okay, so let's go one more step to make this one into the 0. Let's see if I did everything all right. Okay, so that was a negative 4 plus 2i, and I just picked the 4. Yes, it's okay. So what we end up is going to be, you see, if you just simplify that last part that we are going to have, so that's what negative 4 plus 2i, and that give you the result. Just want to make sure that I did everything all right here. Okay, I double check this one. Is a negative 4 plus 2i. Okay, that was the one. And this is going to be your R2 plus 4 times. So I simplify it, negative 4 plus 2i, and this is a 2i, 2 over I, 4 and 4 was cancelled out. So I missed something here, you see? Look at this one, 2 over I multiplied the top and the bottom by I. So I forgot to put the I here. So this would be cancelled out at this level. You see, that's what. There was a negative. It was I missed. So I get the 0, 0. So when I get the 0, 0, you see the top is going to be what? It's going to be x1 plus. So I repeat it here. You believe it. You will see that I arrive at the same answer that I did right at the beginning. So I got the 1 here. Okay, this is it. I got the, so 1, and this is 1 plus 2i over 2i. Okay, 1 plus 2i, and I got the 0, 0 here. So eventually I got a dependent system. So from the first one, we get the x1 plus 1 plus 2i over 2i times x2 equal to the 0. If you break it, you will see that you got the first thing that I did. You break it into the 1 over 2i plus 2i over 2i times x2. So that's the x1 plus 1 over 2i plus 1 x2, and that give you, again, you multiply the top and the bottom by I, that give you, okay, this is going to be the I, it's going to be 1/2, okay, negative 1/2 of I plus 1 times x2 equal to the 0. If you go back and have a look, you will see at the beginning we did have exactly, okay, exactly what I got over here. Okay, that was the 1. So x1 is equal to the, you move it to the other side, is going to be 1/2 of I minus 1 x2. If you go back and have a look, we get this one right at the beginning. You see, negative 1 plus 1/2 I. So what I did, I quickly take the second row, negative 4 times x1 plus negative 4 plus 2i times x2. Give me the same result. So look at this one that I got here. So is it negative 1 plus 1/2 I? Negative 1 plus 1/2 I. Okay, so don't bother right at the beginning. As soon as you form, you pick one of these, that would be fine. Whichever is easier. Whichever is easier to find the complex, your vector and continue. So you don't have, it takes time if you want to get these numbers, and we know that it's true, so why not we use it right away. Okay, so that's it. I'll give you one more example next time, or we are going to see a couple of them in your next quiz, the review one, and they can review and get these numbers. Okay, so I just repeated again what we did. The idea is how we're going to apply the complex numbers for the eigenvalues. So the idea is, as soon as one of your eigenvalues is going to be complex numbers, lambda, its conjugate, lambda bar, is going to be another one. If you find the vector x for lambda, the second vector automatically would be its conjugate. That's it. That's the idea. So we did this one. We did it carefully, and we find out that the lambda is a complex numbers. Automatically, we get the conjugate of the other one. You see, we did have it. But the point is how we're going to find the eigenvectors. We do the same thing that we did before, but a little bit be patient. That's the form of the matrix that we did, okay? You simplify it, don't go on. We know that this is going to be independent matrix, and one of these rows would be 0, 0. So pick another one, it doesn't matter, the first one or the second one. Just pick one of these rows, multiply by x1 and x2, and get your vector right away, okay? So as soon as we get your vector, it's going to be a complex vector, okay? Complex vector. Break it into the complex part and the real part, and the conjugate of this vector is the second one. Don't wait for it. So we just change this sign, so that give a p2. So we did have two eigenvalues, and we find two eigenvectors. That's it. The application, you will see that system of differential equations that I talk about it. It is going to be a case that the solution is going to be complex numbers. We give you a couple of them on your next quiz, and of course one on the final. Okay, have a good one. So what I do is for the next week, I just focus on that system of a differential equation. This is one section. You have one chapter on application problems. I think it's chapter 7. The best application for us is just that system of differential equations, because you use it quite a lot in science. So we spend our time on that one in order to finish everything. Okay, I try to put your, okay, look at this, the test. okay, give you a grade. Then we drop one test, one quiz, okay? Then I'll update the grade book with these new, okay, new points and your assignment, everything. Then if it's anything missing, you email me, I check it for you. Okay, have a good one and take care. Bye-bye.